Alright, so let's start with this topic of rotational kinematics. So just this chapter will help us to go back to day one when we talked about something called kinematics. So after that we did kinematics of particles. After that we did something called dynamics of particles. Now what you got to realize is when I say particle, I don't have to worry about a factor called rotation. And when I say kinematics, I'm talking about the variables used to describe the motion. Okay, there is no force in these kinematic equations. We're not trying to um, tell you the Newton's laws and dynamics or predictions. We're just trying to say the relationships between the variables used to describe the motion. Now in dynamics we make use of Newton's laws to make the predictions. So similarly, I just want to quickly just remind you what you mean by prediction. So basically the position of the particle, let's say in 2 dimensions, as a function of time. That's the prediction, and you will need variables like displacement, in this case, okay, position, position, and then you will need variables like velocity, okay, as a function of time, and you will need variables like acceleration as a function of time, acceleration as a function of time. Now we've discussed this before. We can stop with this list of variables because Newton's laws connects forces in the universe to accelerations, and if we know the forces, then we know the accelerations. If we know the accelerations, we can start from here and come all the way back and predict the position. So that's what we've studied. Now let's see how the picture, some more variables have to be added when you move from a particle to a body. Okay, so let's start with that. What do you mean by a rigid body? Let's take examples. So most of these daily objects, and we'll not let's not choose a very complex. So for example, a billiards ball, or a bowling ball, or a cricket bat, or a simple scale, meter scale, can be examples of rigid bodies in the sense that we neglect the compression and elongation of these bodies. Okay, we say that neglect the deformation. So for example, we saw last time in a photograph where the ball gets deformed during the motion, but we neglect the deformation and we consider the body as rigid. It's a good start to understanding non-particle dynamics. Now, so you have the anything real has a shape, and it's not a particle, so it's a rigid body. What I want you to worry is how do you take care of the shape? Okay, so we'll get to this slowly, but yes, so whether it's a scale, or whether it's a cricket bat, or whether it's a bowling ball, or the other famous example is discs. Okay, what I mean by a disc is okay, this a nice cylindrical object, which could be solid or it could be hollow. Now these are details that are going to be important. Okay, so that means the shape is now going to be taken into account when we do our predictions, right? So this is the background. So now, just for convenience sake, let's take the example of a rigid body as a scale, and this is, I think, where we left off last time. So now you're going to say that I'm going to throw a scale up in the air, and I want you to be able to predict its motion. So this is where we left off last time, and a priori I just want to tell you that this is a difficult problem. Okay, so I just want to tell you that if you just throw some plate up in the air and it starts wobbling in the air, it's not an easy problem. Okay, not easy. Okay, but it's important for you to realize that we're not going to do the problem with all its difficulty. We're going to do a simplified version of this problem, and this is the thing that's there in your syllabus. Okay, so this is actually very difficult. It's not even there till you get to university, so don't worry about it. But what is there in your syllabus is definitely the first step, but very important. And not that it's very straightforward. It's a simpler version of the problem, doesn't mean it's straightforward. So last time actually I introduced this to you, that let's assume that the scale is in one plane. That what I mean by that is that it's in the, let's say it's in it's on this blackboard all the time. Okay, and it is rotating. Let's say throw it up in the air and it keeps rotating. Okay, so this is fine, and then of course it just maybe falls down. Not an issue here, but let it be in the plane, and I hope that I want you to realize this quickly, that it is rotating about an axis which is perpendicular to the blackboard. Okay, this makes it simpler. So if the scale is coming out of the blackboard or wobbling, then I don't want to worry about it right now. Okay, so let's say that you can visualize the axis about which it's spinning. So for example, at this instant, it is, let's say, that rotating about this axis which is passing through this dot but is perpendicular to the blackboard. Pretty much here it's rotating about an axis which is perpendicular to the plane of the blackboard, and this point here, I think you must have guessed, I'm zeroing in on the center of mass. Now the center of mass is very important role to play in this chapter. You might think it's important, but now you will realize that it is even more important, and we'll come to it. But I think what I want you to note is that in our problems in this chapter, this axis will always be perpendicular to the blackboard, always. Okay, and in fact the formulas that we derive will be in that objective. Okay, so the formulas will look much simpler if the axis is always perpendicular to the blackboard. So let me give you another example. So let's say that a car tire. I mean, we've played with some kind of tires, and these tires are rotating. Okay, constantly rotating. But let's say that it goes in a straight line, and it doesn't wobble. That means the tire never comes out of the plane of the board. No wobbling. Okay, then I think we are in business with the things that we learn in this chapter. Okay, so what that means is that, now for example, what is the axis about which it is rotating? The center of the axis is this, center of the axis is this, center of the axis is this, the center of mass is somewhere here, but the axis is perpendicular to the board, right? So now these are two good examples to keep in mind when we're talking about rotation. Okay, and what I want you to sort of realize here is that for telling me what is the status of the scale, you could tell me the position of the center of mass. For example, you could tell me that okay, the center of mass is here. Oh yeah, implicit is that we all know where the origin is, so you could tell me that this is x and then this is y of the center of mass. Already I know where the yellow spot is, and perhaps you could tell me this angle. Okay, let's call it alpha. Oh, alpha is a bad choice. I'm very sorry. Alpha is a really bad choice. Let's call it theta. Theta is the standard choice for telling us the orientation. Let's say you can tell me theta about the x-axis. So here you go. You tell me xcm, you tell me ycm. They all change with time, and now this additional variable theta t. Right. So this is the new kinematic variable which is now being added to what we already know, and together it tells us where the scale is. So are there laws which help us to predict this? Well, you already learned them. Answer is yes. You already learned them, but let me just write it here. We discussed it last time. Force external is equal to, well, let me just write it like this: acceleration of the center of mass. There's another way of writing it. Okay, dp by dt. Oops, so I just realized that I forgot to tell you that this whole thing is considered as a system, and this is very important. You must realize that now the scale is not a particle but a system of particles, and this is valid for a system of particles, and therefore this is going to be our primary weapon to understand the acceleration of the center of mass and therefore its position and so on. So let's summarize. I think we need to now tell you, okay, I just want to highlight this. We're doing a simplified version of the problem. Where the axis is always perpendicular to the blackboard. And blackboard is the place where this object is moving. It's not coming out of the blackboard. That's number one thing. Number two thing is, I need to tell you, okay, let's just call it the z-axis, or parallel to the z-axis maybe, because this the notation that is used in the book. They always say that the axis is parallel to the z-axis, and what they mean is that the blackboard is the x and y-axis. Now with this notation firmly in your mind, you have a coordinate system. What you're trying to do is predict the x center of mass, y center of mass, and theta, which is the angle, let's say, with the x-axis. Of the scale. So with these, the question to ask is, Can you predict? And the answer is yes. And that's what we have to learn slowly. That is, you predict this with all the theory that we've learned so far. That is this system, mind you, and the system is a whole scale, and that is equal to dp by dt and dt, or it's important for you to write it also like this, very important to write it, mass of the scale and the whole system of particles, which is the whole scale, into acceleration of the center of mass. Very important to remember this in complete together. You got to realize while they're the same thing, we might use a different form sometimes. And before we start figuring out what are we going to do to make this prediction, we need to spend a little bit of time as to understanding the variable itself, and that is what is called rotational kinematics. Now mind you, how many variables do you want is interesting. So for example, so let me just okay, so far it's good. So we still don't know at this stage how are we going to make this prediction. What I'm trying to tell you is that once you do that, you're done. But today's focus is not on how to predict this, but to understand the variables. So for example, what are the variables we needed to study the subject? Okay, let's talk about 1D. Okay, you needed x, and then you needed vx, and then you needed ax, and you need to stop here. The reason you're stopping here is because the law is ready to enter into the action. The law of physics here is F is equal to ma. Now the law requires a, so you got till a, and there's no need to go ahead. Now the thing is, you know how to come from here to here, and you need to come because your aim is here. Then you need to know how to come from here to here. So all of this is kinematics. So let me write it. How do I do this? Yeah, very important. So you need to write this. Can I come from? This is very easy. This is the position. You can easily visualize this. You understand this. Okay, position with an origin and all that. Okay, this is this. Very important for you to write it like this now and make sense out of it. Okay, and if you want, you can also write it like this: the change in the position and the change in the time, but take this time interval to be small. This by the way is instantaneous velocity, so therefore we say v is a function of time, a is a function of time. What about ax is a function of time? This is dvx over dt. T. If you want, you can write it like this, and it's easy to understand what we're trying to say. There's a change in the velocity depending upon the time interval, but we try to keep the time interval small. Okay, now you get this itself from the law, and you do know how to go backwards. That's okay, you do know how to go backwards. Okay, and that's the end of the story, right? So what's the how do you go back? So how do you go back is, okay, now this is called differentiation. Okay, and you go back by integration, so this should not worry you. But if you want a little bit of a concrete example, what we do is, to reduce our dependence on calculus, we take the case of constant acceleration. You got to keep in mind that, listen, you got to keep in mind that this may be important, but it's a simple case, and probably you're going to come out of this comfort zone of constant acceleration with the help of calculus, which is going to take a little bit of time. But nevertheless, it's an important case, and see what happens if the acceleration is constant. What happens when the acceleration is constant is that the backward journey is very easy. What I mean by this is, let's say it's constant. Okay, so basically you're saying that this quantity here is constant. Okay, I'm just calling it A. Okay, yeah, I'm just calling it A. It's a constant. Okay. Now, what you realize in this particular case, it's very easy to guess that V is equal to U plus AT. And if you ask me, hello, why is this true? I'll say, look, why don't you differentiate it? Okay, so this is a constant, by the way. U is a constant. Differentiate it with respect to time. You see, this is 0 plus, and you know that the derivative of AT is A. So that's one way for me to convince you that this is true. Okay, all of this will be too easy for you if you have learned a little bit of calculus. But for me right now, okay, once again I repeat, this is an important case of acceleration is equal to constant. It's a small sub-case, but important sub-case to get us a feel that we're basically trying to convince you that, look, coming back is not really difficult. Now what? Now can you go further back? Okay, and again it's quite easy for me to tell you the end answer, and we are remembering the end answer in a way which is best. X final minus X initial, we know what that is. X position is equal to ut plus half at square. Again somebody tells me, look, how do you know? How do you know that this is right? Well, same answer. Why don't you do dx by dt? Now you do dx by dt and you'll actually get, here it is u and here it's at, because the derivative of t square is 2t multiplied by a by 2 and you'll get 80. So there you go. I have two important formulas. The essence of the formulas is that I've gone backwards. In a simple case, but end of the day I have all my important so-called kinematic formulae. Okay, but if the acceleration is not constant, then you got to remember this and this, and okay, the whole thing actually might be a good thing to the whole thing is nice to remember. Okay, so you got to remember this, and then you got to remember that the backward journey is a little bit more calculus, a little bit more, which is quite easy. So one more time I repeat that you can stop here because this is the law. So what's the story, same story that has been written out on this page for theta, okay, which is the variable to describe rotation, right? So this is what I'll describe in the next video. It's all very simple, but the story will be similar. You tell me what are the kinematic variables like this, like this, like this, that is used to describe rotation, and then you can say, why does the story stop there? Because of a new law. Okay, and then because of a new law. Okay, and then let's do this backward journey by a special case, which is a simpler case, but you better know it, and write down the formulas. And surprisingly, or actually surprisingly, it's very similar to this, and that's the connection that you have to make, that because it's so similar to what has been written on this page, the last word is that the similarity is so striking and so easy to remember. The story is almost the same. So rotational kinematics is easy. So let us get to it in the next video. But it's easy, and I think Rusnick and Halliday that I've uploaded, the book that I've uploaded is a short form, right? The more older version. I think the older version has done a beautiful job of doing this quickly and nicely, and you will get whatever you want from here. And then you can just do, I think what you should do is you should do a few solved problems before you jump into the exercises, and you can do as many exercises as you like. If you look at some of the problems, and if you find some one or two elude you, then you can just let me know. But I think it's important that the solved examples are very clear in your head. Alright, I'll catch up with you in the next video.